So greetings of the day. I am Dr. Arijit Mondal, the Assistant Professor from the Department of Physics, Madanpalli Institute of Technology and Science. Today I am going to discuss the Hall effect. So these are the outlines of my presentations. So first I will discuss the energy bands of solid. After that I will discuss the how classification of materials are done using the energy band gap of a solid. After that I will discuss the types of semiconductors, and after that I will discuss the Hall effects, and I will conclude my presentation by discussing the applications of Hall effect. So first, the energy band of a solid. For an isolated atoms, the electrons occupy the discrete energy level. See here, this is an example of an energy state of an isolated atom. Here the 1s state, there are 2 electrons are there, and 2s state, 2 electrons, and the 2p state has the 6 electrons, and the 3s state is completely empty. This is but when the atoms comes together to form the solid, the atomic orbitals overlaps and the energy levels of the individual atoms spread out and forms the energy band. See here, this is demonstrated from this figure. See here, the when the atoms are far apart, there is interparticle or the interparticle distance was large. In that case, there is no splitting of energy level. Energy levels were still discrete. But whenever they come closer and form the solid, the energy after some interparticle distance, their energy levels get splitted. So how many number of energy levels it will form? It will form for the 1s case, let's say the 2 electrons are there. 2 electrons. So for the n atomic system, the 2n number of energy states it will form, and this 2n energy state, one level correspond to this 2 state, because one is for spin up and another is for spin down. So the n number of energy level will be there and 2n number of states will be there. Similarly for the S2s state also the similar situation, but for the p case there are 6 number of electrons are there. So 6n, for the n atomic system the 6n number of energy level will be there. Here energy state will be there. As a result of this, the 3n energy level will be there. But for the 3s state is completely empty, 3s state, because there is no electron at all. So now what is the valence band? Valence band is the topmost occupied energy band, is called the valence band. See here, for the single atomic state, the 2p state was the topmost occupied energy state. Whenever it will form solid, the 2p state will be completely occupied and form the valence band. So this is the valence band of this solid. This is the valence band here. And now what is the conduction band? Conduction band is the energy band just above the valence band. That is called the conduction band. So this is the conduction band. 3s band was 3s state was completely empty. Whenever it forms energy band, there is no electrons at all. But the states are 2n states are there also, and the energy level, but these are completely unoccupied. So this is the conduction band. So valence band is fully occupied for the case of semiconductor insulator, but for the electron, that's why electron cannot conduct in normal situations. So for the conduction occurs, electrons should go from the valence band to conduction band at all. So what is the band gap? Band gap is the difference between the energy of the top of the valence band and the bottom of the conduction band. So this band gap, what is the how one can classify the materials based on this band gap? So based on this band gap, we can classify the materials by using band gaps, decide whether the materials is conductor or insulator or semiconductor. This is the typical energy band diagram of a conductor. See, conductor, the valence band and conduction band almost coincided. That means there is no forbidden energy gap was there. But for the case of insulator, the energy gap was very high, that is almost 7 eV nearly, the forbidden energy gap. But for the case of semiconductor, the energy gap is 1 eV, that is very small. So semiconductor are those substances whose electrical conductivity lies between conductor and insulator. Now based on this charge carrier, this semiconductor classified into 2 types. One is for the intrinsic semiconductor and another is extrinsic semiconductor. So what is intrinsic semiconductor? An intrinsic semiconductor is the chemically pure substance of a semiconductor. At absolute zero temperature, the intrinsic semiconductor has no free electrons, so do not conduct electricity. So for conduction happens, electrons need to go to from valence band, go to conduction band from valence band. So at 0 Kelvin, see here in this typical diagram, the energy level is completely occupied for the case of valence band. Electrons are completely occupied, but for the conduction band it is completely empty at 0 Kelvin. But at higher temperature, what will happen? Higher temperature, some of the electron will go from valence band to conduction band. As a result of this, some current will flow, and this current depends on the temperature of this material. Now, what is the extrinsic semiconductor? Extrinsic semiconductor is the semiconductor that has been intentionally doped with small amount of impurity atom to the pure semiconductor. In addition to specific impurity atoms, the extra charge carriers, what will happen? That will give you the more number of electrons, and as a result of this, the conductivity of the system of the semiconductor will improve lot. So there are two types of extrinsic semiconductors are there, depends on the doping. One is N-type and another is P-type. So what is N-type semiconductor? N-type semiconductor is created when by adding the pentavalent impurity atom. What are the pentavalent impurity atoms? Pentavalent impurity atoms are like, the examples of this are like phosphorus, arsenic, antimony, etc. For the N-type semiconductor, the majority of charge carriers are electron. So what is happening here? See, let's say for the case of example, for the case of silicon. Silicon case, the electron configurations are like this. Here the valence electrons are the 4 number of valence electrons are there. For n equal to 3, there are 4 electrons. So 4 valence electrons are there. So 4 valence electron are Si. So whenever you drop the pentavalent impurity atom, so out of this 5 electrons, the 4 will make the covalent bond with the Si, with the free electrons of Si. But another one cannot do. As a result of this, it will give you, this pentavalent impurity atom will give you the one free electron. That's why so as a result of this, its conductivity will increase a lot. Similarly, for the p-type semiconductor, what is happening? P-type semiconductor is created by adding impurity of trivalent atom. The trivalent atom likes the boron, gallium and indium. So whenever you dope the p-type semiconductor trivalent impurity atom, these three electrons will make the covalent bond with 3 of the Si atoms, 3 of the Si electrons, but others remains non-bonding. So as a result of this, that will form the hole. Now, what is the Hall effect? So if somebody has given you a specimen, let's see whether a semiconductor is given to you and you don't know whether it is N-type and P-type, how you can experimentally determine whether it is N-type and or P-type? That you can determine from this Hall effect. So what is the definition of Hall effect? Hall effect is if a current carrying specimen is placed in a magnetic field that is perpendicular to the direction of current flow, the electric field is developed in the direction both perpendicular to the current flow and magnetic field. That is called the Hall effect. This phenomena is first discovered by Hall. That's why, according to name, this phenomena is called the Hall effect. So here I have taken, in order to demonstrate the Hall effect, I have taken a N-type extrinsic semiconductor. See, this is an N-type extrinsic semiconductor. This has the length L with W and thickness T here. Thickness is T. So, here the magnetic field I have applied along the Z direction. Therefore, I have denoted it to Z. That is, I have denoted it to BZ. And see, here the current, I have applied battery here in this direction, that is in X direction. So the current will flow in that direction. Whenever if you apply potential difference, the current will flow in that direction. That means electron will flow in opposite direction. So now the currents moves from positive terminal, that means here, to negative terminal of this battery. As a result of this, the electron will flow in the negative direction or the opposite direction. That means in negative x direction. Now, in the presence of magnetic field, the electron will experience a Lorentz force, we know. What is the Lorentz force here? What is the magnitude of Lorentz force? Lorentz force magnitude F equal to minus E cross V cross B. V is the direction of electron, C here, and B is the magnetic field, that is along Z direction. What is the direction of electron? As I said, the direction of current is, what is the direction of current? That is in positive x direction. So direction of electron is in the negative x direction. Now, the cross product of this give you the F. What is the value of F? What is the direction of F? That is equal to, that is given by the right hand thumb rules. See here, that is V is in minus I direction, B is in K direction, so its cross product will give you in negative Y direction. So force, the Lorentz force, the direction of Lorentz force is in the negative Y direction. Now, so as a result of this, there is the accumulation of negative charge on the left side of this material at the positive charge, but the right side there is still some positive charge. As a result of this, the electric lines of force will go, as we know, the lines of force will go from positive to negative side. See here, this direction, that means minus y direction, is there is some electric field will produce, that I have denoted by chi y, that gives rise to a force. What is the direction of this force? The direction of this force will act on the electron. So electron has charge negative. So the direction of this force is this plus y direction. That means in j direction. What is the magnitude of this force? That is E chi y. That is on the positive y direction. Now at equilibrium, what will be happening? At equilibrium, these two forces must be balanced. That means minus E Vx Vz equal to E chi y. That means, see, what is the Hall field? The EH equal to chi y equal to minus Vx into Bz. This chi y or EH I have denoted by EH, that is called the Hall field. That is called. So, now the current density we know, the Jx equal to NE So here the current I have applied along the x direction. As a result of this, current will flow in x direction. As I said, the electron will flow on the negative x direction. So what is the current density along this direction? That is equal to Jh equal to NeVx. What is N? N is the concentration of electron, E is the charge, magnitude of charge, and Vx. What is Vx? Vx is the drift velocity along x direction. Now, the current through the n-type semiconductor along x-axis is, we know, I equal to Ne Vx into A. What is A? A is the cross-sectional area of this material. Now, what is Hall field? The Hall field expression we can write, that is equal to EH equal to minus Vx Vz. If we plug this here, if we plug the value Vx here, that will give you the minus Jx Vz by Ne. What is the direction of this Hall field? That is in minus y direction, as I said. So that is equal to RH Jx into Bz. That is along j direction. So what is RH? RH equal to 1 by Ne. Minus 1 by Ne. That is called the Hall coefficient. This RH is called Hall coefficient. That determines the material, whether it is the N-type semiconductor or P-type semiconductor. For the case of N-type semiconductor, this RH is negative. But for the P-type semiconductor, the RH is positive. Because P-type semiconductor, the majority carriers is whole. So, in that case, this RH is positive for the case of P-type semiconductor. Now, how one can define the Hall coefficient? So, Hall coefficient RH equal to EH by Jx Bz. That means, what is Hall coefficient? That is the Hall field developed per unit electric magnetic field along the z direction and the current density along x direction. That is the definition of Hall field. Now, what is magnetoresistance? See, there is a electric current we have applied along this direction, x direction. There is some xi x, the electric field will be there, because the two ends there is some potential difference. So the ratio of this xi x divided by jx, that is the current density along this direction, is called the magnetoresistance. Now what is Hall voltage? So Hall voltage, as a result of this Hall field, the Hall voltage will generate between the two ends of this semiconductor. See here, that is the VH, I have denoted here the VH. Now, see what is the Hall voltage? Hall voltage VH equal to EH cross W. W is the width of this semiconductor. This is the width here. So now the Hall coefficient, how to write in terms of Hall voltage? So we know what is RH. RH equal to EH by JX into BZ, right? So what is EH? EH we know that is the Hall coefficient. What is JX? JX equal to current density. So that is equal to current per unit area. So that is Ix by A. Now what is A? A is the area of this material. So what is area? The W is the width and T is the thickness here. So T cross W will give you the area. So VH now, what is this? So Ix, now we can write this like this. So Ix, if we multiply this, so EH equal to VH by W, we know from this equation. So the VHT by IXVZ will give you the Hall coefficient. So this way we can write the Hall coefficient in terms of Hall voltage. So what is Hall voltage here? The Hall voltage VH equal to RH IXVZ by T. So VH equal to IXVZ RH by T, right? So here the VH is proportional to, inversely proportional to T. That means VH is proportional to 1 by T. So if we increase T or the thickness of this material, the Hall voltage will decrease. Now, what are the applications of Hall effect? There are lots of applications of Hall effects, and what are the importance? Now, its importance is to determine the types of semiconductor. If you know the Hall coefficient, that is equal to RH equal to minus 1 by NE. If you know the N type, for the case of N type semiconductor, this is negative. If you get the Hall, if somebody has given you a material and its Hall coefficient is negative, then you can conclude the material is N type extrinsic semiconductor. But if somebody has given you a material whose Hall coefficient is positive, you can conclude the material is P type semiconductor. And how to classify the materials? For the case of the semiconductors, the RH is very high. That means Hall coefficient is very high. And for the RH is very low for the case of metal. Why RH is very low for the case of metal? Because the metal RH is proportional to 1 by NE. If you increase N, RH will decrease automatically. So for the case of metal, there are lots of free electrons. So that means N is higher. That means RH is very less. So for the case of metal, this is low. For the case of RH, RH is infinity for the case of insulator, because there is no free electron at all for the case of insulator. All the electrons are bound for the case of an insulator. That means RH is infinitive here. Now, see how to determine the carrier concentration. So if you know the RH and we know the amount of charge, what is the value of E we know. So N you can calculate. If you don't know the carrier concentration and you know the Hall coefficient of this material, you can automatically calculate this. Now how to calculate the mobility of this material? Mobility. From the conductivity nu and the Hall coefficient RH, you can calculate mobility like this. You know J equal to the current density, that is equal to NE mu. N is the number charge density, E is the amount of charge, and mu. What is mu? Mu is the mobility here. So mu divided by RH. So NE is nothing by 1 by RH. So mu by RH will give you sigma. So mu equal to sigma cross RH. That is the mobility. So why semiconductor? So this way you can calculate the mobility of this material also, if you know the Hall coefficient and conductivity of this material. So why I have chosen the semiconductor, as a material to demonstrate the Hall effect, and why it is most suitable for the case of semiconductor only rather than this metal or insulator. See, for the case of metal, there are plenty of free electrons. As a result of this, it collides very rapidly. As a result of this, what will be happening? The mobility is lower for the case of for the case of metal. As a result of this, see here, the Hall coefficient is proportional to this RH is proportional to mu. So as the mobility is lower, so in that case, definitely Hall coefficient is lower for the case of a metal. That's why for the case of metal, as the case of metal, we don't use the metal to demonstrate the Hall effect or to experimentally study the Hall effect. We use only the semiconductor. This number of free electrons are less for the case of semiconductor. See, one thing is, for the case of mobility, sigma, that is equal to any mu. So mu, although the n is higher for the case of, keep in mind, n is higher for the n is much higher for the case of conductor when mu is lesser. That's why sigma is higher for the case of conductor. That's all about my presentation. So thank you.